Welcome back to statistics, everybody. We are getting into our next set of inferential statistics. This section is going to be about looking at mean differences, and there are two sets of stats that fall under that heading there. So we're going to be looking at the first set of them called t-tests this week. So here's what we're going to do in this video. We're going to talk about the basics of t-tests, kind of like we did with chi-square, just set the basics for what the statistic is. And then we're going to get into the first of the t-tests called the one sample t-test. Now, what are t-tests generally speaking? Well, just like the chi-square and the rest of the stats you're going to learn, they are inferential statistics, right? Drawing conclusions about a sample and applying them to a population. Inferential statistics are used in hypothesis testing, and so t-tests fall into that as well. And here's the thing that's unique about t-test. When you're comparing means, you would use a t-test to compare the means of exactly two groups. Not more than two, not one, exactly two. Now, the three types of t-tests that we're going to cover in this area, and we're going to cover the first one, the one sample, in this video. So let's get into what the one sample t-test is, and we'll start out with the what and the when. Okay, so what is it? So the one sample t-test is when you want to look for a significant difference between the mean of a single sample and the mean of the population it was drawn from. So in this case, the two groups you have are not two different groups of people. It's not one group of people measured on two variables. It is the sample compared to the population it was drawn from. So that's when you would use it, when you have one sample with one variable of continuous data, and you want to take the mean of the sample and compare it to the mean of the sample's population. All right, that's in the case when you would use a t-test here. So the two groups, quote unquote, the two things that we're comparing here is the sample mean to the population mean. Those are our two means that we're comparing with a one sample t-test. Now here's our general question, kind of set up a context for us to understand the one sample t-test further. So our general question is, well, let's have a scenario first. Let's say that you work for student life and you work in the dorms, and you are tasked with determining if the average student rating of students who live in the dorms is different than neutral. Okay, so you're given this general question to investigate. Do students rate the dorms differently than neutral? So let's say you go out and you give a survey to 100 students, a questionnaire, right? And everybody gets a final score on the questionnaire ranging from 1 to 7. 1 indicating strongly dislike, 7 indicating strongly like, and 4 being neutral. So our general question then, we can be more technical in phrasing our research question with the following. Is the average student rating significantly different from a presumed average rating of 4 from all students? So let's look at some characteristics of the research question here that indicate one sample t-test. One, you're looking for a difference between two groups. Now, as we said before, the two groups in a one sample t-test is the sample and the population. So things that indicate that here would be the average student rating. That's referring to the sample, right? The sample of 100 students. And then all students would be from all the students who live in the dorms. So that would be our population mean that we're comparing to. Now, we're looking for a difference, okay, between the means. So you'd see a keyword different there, especially with the technical term significantly different. And average. Average is going to be referring to our means. We're looking at the averages here. We want to see if the average of the sample student rating is different from the average rating from all the students, okay? And lastly, we see that one sample is mentioned. That would be the 100 students, okay? Now, the last thing is that we want to make a comparison to the population. Now, the population is these keywords here, the presumed average rating of 4. Now, remember, the reason we take a sample is because we don't have access to the population. So you might think to yourself, how can we compare the sample mean to the population mean if we don't know the population mean? Because we can't study the population directly, right? So that's why it has this keyword in the question, presumed average rating of 4. Let's say that for some reason we have, let's say that we have reason to think that the average rating from the population of students in the dorms is 4. It's about neutral. So I presume what the population mean might be. Researchers do this a lot. They have, based on prior work or some theory that they're working off of, have a reason to presume what the population mean could be. So then they take what they presume the population mean is, and then they compare their sample mean to that presumption there. So we don't actually have the population mean, we're presuming what the population mean is. So you have to make sure that you include that language when you're specifying your technical research question. What is the presumption? What is the presumed population mean? And usually the context in your assessments, like when you're working on a one sample t-test problem, the context will indicate what the presumption is you should have to specify in the question. So what are our variables here? Well, we have one sample, and we usually have one variable with that one sample. So we have a single X variable with a one sample t-test. So in this case, the sample, the X variable is student ratings, okay? And we know that student ratings were measured on a scale of 1 to 7. Okay, so that's how we're measuring it. And notice how that is the continuous measurement here. When you have categorical, it's something slash something else, indicating either or indicating separate groups. When you see dot 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 and ellipsis, that's usually representing, oh, it's a continuum. We have 1 ranging to 7, right? Because when you're working with a t-test, you're working with continuous data that's being measured there. Okay. So that's when we have a single X variable, and it is the student ratings, right? The student ratings from all the students, the presumed average of 4, and then the student ratings of the sample of 100 students that we're working with. Now, how do we actually do this test? How do we run a one sample t-test? Well, just like in the chi-square where you had a chi-square score that you had to calculate, with all 3 t-tests, you have to calculate something called a t-score. Now, the thing about the t-score is that it always represents the same thing in all 3 t-tests, but it's calculated slightly different because each t-test is utilized in a slightly different scenario with different parameters, okay? So the t-score represents the same thing for all t-tests, but it's calculated differently for each t-test. This is how it's calculated for the one sample t-test. You see on the top here of that t equation on the left side, you have t equals the sample mean minus the population mean over, if you remember what the symbol is, this is standard error, okay? So the top part is the difference between the means. That's what we're interested in, right? So the t equation has that included. We want to know how different are my 2 means from each other. So the one sample t-test, how different is my sample mean from the population mean? And then the bottom part is factoring in sampling error. We always have to account for sampling error. We have to account for how different is my sample from the population when calculating my t-score. Now, how do we calculate standard error? Well, that's the equation you see on the right-hand side. So standard error is equal to the standard deviation of your sample divided by the square root of n, which would be your sample size. Okay, so you take the size of your sample, square root it, then divide your standard deviation by that square rooted sample size. So you put that on the bottom, and then you take the standard error and divide the difference between your means by that, and you get a t-score. So what is a t-score representing? Well, the t-score represents the statistical difference between 2 group means while factoring in sampling error. So it's representing how different are your means from each other while also representing how much sampling error that you have. That's the thing about statistics that makes them useful. They're nice and clean. Rather than having to have 2 separate numbers, we can calculate one number that represents 2 things at the same time. How different my means are, while also how much error do I have in the sample that I'm working with. So in a one sample t-test, the t-score represents the difference, the statistical difference between my sample and population means specifically. So let's put this in practice here and see how the t-score can be calculated with the scenario that we're working with. So again, I have 100 students take a questionnaire, and I want to know, is their average rating different from 4, which is about neutral on that questionnaire. So calculated the mean for our sample. So let's say that I give you a mean of 4.51 and we have a standard deviation of 1.94. So 1.94 would indicate that on average, the 100 students are deviating from the mean of 4.51 by about 1.94 points, you might say, on the questionnaire. Okay, so then we've got our 2 numbers we can work with here. So now we need to find n and our population mean. So what should you fill in those? Well, n should be 100. We know that from the context, okay? And the population mean should be 4. That's our presumption. So now what we have to do is we have to do our calculation. So pause the video, try calculating the things that you need to, and then continue on to see if you got them right. Okay, so our sample is 100, our population mean is 4. So first we have to find our standard error. So our standard deviation is 1.94, that goes on top, and the square root of the sample size is 100. So that goes on the bottom. And the result you should have gotten is 0.194. So that is our standard error, representing how much sampling error we have. Remember, to interpret sampling error, or standard error, the closer it is to 0, the less sampling error you have. The further from 0, the more sampling error you have. 0.194 seems to be closer to 0, right? It's less than 1. So it may be on the better side of being smaller. So let's just keep that in mind. So now we have our t equation, okay? And what you should have gotten is you put 4.51, the sample mean, minus the population mean of 4 divided by the standard error. You should have gotten a t-score of 2.628, okay? So 2.628. Now that number is representing how different your sample means are while also factoring in sampling error, okay? So let's kind of tie that together. So again, remember we have the top part is the difference between our means, the bottom part is sampling error, and then we have standard error is the measurement of sampling error, okay? So a bigger t-score indicates a bigger difference between the means, okay? As we said before, the bigger the t-score, the bigger the difference between our sample and our population means, okay? Now, when you have standard error, a bigger standard error results in a smaller t-score. Let me show you how that works and why that's going to be important. So, okay, the more sampling error you have results in a bigger standard error, which results in a smaller t-score, okay? So what happens if we have a smaller sample size? Now remember, if you remember from the inference section, the way to decrease sampling error is to have a bigger sample size. So if we were to decrease our sample size, that would result in a larger amount of sampling error. So let's see what happens when we do that. So let's say that we cut our sample in half and only surveyed 50 students. Well, then we put 50 in the square root of the bottom of the standard error equation. We get 0.274. Notice how sampling error got bigger now. It went from 0.194 to 0.274. Okay. Now, if we plug that into the t equation, you see that we get a t-score of 1.861. Our t-score went down. Okay. Before it was 2.628, but when sampling error increased, our t-score went down. So the more sampling error we have, the lower our t-score. Now, why is this going to matter? When we are testing our t-score, just like the chi-square score, for statistical significance, a bigger t-score is more likely to be statistically significant. Now, if your t-score is smaller because you have a large amount of sampling error, that could increase the chance that it might not be statistically significant. That could increase the chance that it would just be a likely result, okay? Because you have a bad sample, right? So we want our sampling error to be as small as possible, so that way we can make sure that our t-score is just representing the difference between our means while factoring in as little sampling error as possible.